Um, my name is Jongho Park, and welcome back to the Signals and Systems lecture. Okay. In the last lecture, we have been through some interconnections of systems. We basically looked at some fundamental signals and then we entered into the system property. And we started with these interconnections of systems because there isn't just one system, but there can be a lot of systems hanging around together. So there is a relationship which is called cascade, and then the parallel, and then the feedback, and we observed something called negative feedback because of this sign here. And assuming that we are in the Laplace domain, which we haven't learned yet, but assuming that we have derived the equation which we can combine all these together into one system. So we have that definition here, and I ask you to do the same thing if this sign changes to the plus sign. Okay, and we finally entered the system properties subsection, and we start with the memoryless. So the memoryless, as you can see in this equation, the system is set to be memoryless if the system's output for each value of the variable at a given time is dependent on the input at only the same time. Okay, so this is the point here for the memoryless definition. So it is affected by the input at the same time. Okay, then you can say that that system is memoryless. So if I may have some examples, y equals x squared for the continuous time, or also y equals x squared for the discrete time is memoryless because they depends on the current time only. Okay, so these functions or these systems can be called memoryless, and maybe let's have something that is not memoryless, also known as memory. So if I want to do the integration all the way from the negative infinity to the variable t, and let's say we have this squared inside the integrator, then you can verify this as a accumulation, right? So I have to integrate all the stuff from the past to the current time. So this is an act of accumulation. So we can say this is not memoryless or memory. Also, we can think of a simple example for another memory system, which is a unit delay. Okay, so I think I have to add this accumulation. It's a sort of accumulation here. And the last example for the system which is not memoryless is a unit delay. So now we will go back to this discrete time, and if we have only one delay, one amount, then we can say it as this right here. So we have an output which you have to shift the amount of 1 from the input. So this is called a unit delay. Unit delay function, unit delay system. And obviously, we can say that the output is affected by the previous input. So you cannot say that it is affected by the input at the same time. So this system is also not memoryless. Okay, so you can have some examples to distinguish between a memory system and a memoryless system. Okay, and we have another system property which is called invertibility. And the definition is as follows. If a system is invertible, then an inverse system exists. When cascaded with the original system, yields an output, let's say W, which is equal to the input, I will say Xn, to the first system. Okay, so we may have a long definition, but if I plot this, if I plot it, which is about this definition, then you'll get it. So if I have an input to the first system, so I will say that as an original system. And then obviously I will get the output, which is denoted as Yn. And the definition of this invertibility says if I have an inverse system which is cascaded with the original system, so if I want to have a interconnection which is a cascade relationship, then I should put an inverse system here. It's not parallel, it's not in the form of feedback. It should be cascaded. So I'm just following this definition, and if it's cascaded with the original system, then it will provide or yield an output. So the output of the original system is an input to the inverse system, which now has an output, which is called Wn. And a system is invertible if this Wn equals Xn. Okay? So it's kind of like, can you produce the original signal by having a system which is called by having a system, if you can reverse this output to the input signal, then this system is called an inverse system. Okay? So I think you can have a much better understanding with this picture. And let's do some examples again. Okay, I think I want to do the example with a system which is invertible first. Okay, an inverse system, I will use this thing, -1 on the top, which resembles the inverse of the matrix. Okay, so I think I will use this notation. Let's find out some examples for the invertibility. So if I say if a system A is y equals 2x, then, okay, so we are having it for the first time, so I think I'm gonna draw it. So if I put x, and the original system is 2x, right? And what system would I have to make this to xt again? So if we put 1, then this produces 2, and I want to get back to 1. Then what should I do? You have to multiply it by a half, correct? So if I just multiply it by 0.5 times x, then it'll become an x again. So I can say that this system is invertible, and that inverse system can be defined as yt equals 1/2 of xt. Okay, so this is obviously an inverse system. And one more system with invertibility. What about the integrator? Yt is performing an integration from -infinity to t of x tau. I will give the variable tau as an variable for the integration. Okay, let's do it one more time. If I enter x as an input for this integration, what can you do it to reverse it to xt again? I did the integration, and then you do a differentiation. You get the derivative of the output of this integration. Then you will get the original input. Correct? So this here, I may say it as this differentiator. So if I put it in words, the inverse system can be thought of as the derivative of x with respect to the time. So the integrator, so this is called the integrator. And this is called differentiation or derivative. Okay, so an integrator is definitely an invertible system. Then what about the differentiator? What if we want to analyze if a differentiator, whether a differentiator is an invertible system or not? So what makes a difference with this order? I mean, obviously we know that if we differentiate first, and if you want to reproduce the original system, you have to do the integration. So if I draw it again, if we do the integration first, if we do the derivative first, and then obviously we want to have the integration to get back to this original signal. But there is a huge difference between these two, which is about the result of the integration. If you do the integration, if I do, so if I do this integration from minus infinity to t, then what will be produced along with this xt? There is a constant from this integration. So this thing never happened. This thing happened here, right here, but this constant value vanishes due to this integration, which is cascaded right next to this integration, right next to this integrator. So we have this, I think I miswrite it. I think maybe I will say it with large X. Okay, so large X is defined as the integration of xt. Okay, so this is a temporary stuff. I want to focus on C here, even though there is a constant value here also, but this constant value will be removed by this integrator, which gives the original system in the final step. However, in this example, whether the differentiator is an invertible system or not, here comes the derivative first and then the integration. So there is a constant for the result. Therefore, these are not the same. We cannot guarantee that these are same. So, in fact, in general, differentiator is not invertible. However, we can say that we can say it like this: a differentiator is invertible. Generally, it's not. However, it is invertible only for the class of signals, xt signal with minus infinity of that signal being 0. If I limit the signals with these, then this constant also vanishes, right? And only remaining thing is this xt, which is equivalent to the very first input. So I can say the differentiator is invertible with only this kind of signals. However, in general, it's not invertible. Okay, so I think this is very important to distinguish between these two. Okay, so please think about the difference between these two. And maybe I can also have some example for additional examples for a non-invertible system. Okay, so the very first thing that comes up on my mind right now is a system A, which is just 0. No matter what input comes in, it produces 0. If you progress the signal, the input signal, the random input signal through this system, it produces 0. So with this 0 here, okay, I will stop drawing this because now we know what's happening. So if I have 0 here for this system, then there is no way that we can manage this 0 value to reproduce this input. So this is a very simple example for non-invertibility. And also, it's the system with x squared. Why is this system non-invertible? Can you think of it? Okay, I think I'm gonna use this one more time. So if I have some input and have this input squared by this system, then you'll have a squared system. And someone can say that we just square root it, right? What about an inverse system to conduct a square root? When you do this, we have no idea what the sign of this input is. So if I have a minus sign or a plus sign for the input, no matter which one it is, it produces a positive value after this original system squared. And when you do the square root, then you always get the positive value. So with this positive value, you have no idea the sign of the original input. So with this definition, with this description, this system is also non-invertible. It's not invertible. Okay. So we can have the same absolute value here with this inverse system. However, we don't know what the sign of it is. So it belongs to non-invertible system. Okay, this was about some invertibility. And another one I would like to introduce is about the causality. Okay, I'll write the whole statement down and then talk about it with you. The definition is as follows. A system is said to be causal if the output at any time depends on the values of the input at only the present and past times. So if I erase this, then the statement is the same as the one with the memory list, right? So it's very similar, but now we include this past thing. So if system is causal, you cannot anticipate the future inputs. Okay? So it is not dependent. So it does not depend on the future inputs, only the present and the past. So an example of, I will have two examples. Now I'm gonna come up with this discrete time case. So I think we have an easy example here. So, by the way, these are called moving averages. This is like we average the stuff of the input by its mean, right? So we have three values, so we have to divide it by 3. This also to get the outputs, and these are called moving average. It's a very popular filter. And if you look at the first one, this output depends not only on the past and the present, but the future of the input. So this is a system which is not causal, right? However, this one only depends on the past and the present. So this system, you can say causal. So I think I will have just this example for the causality. Sorry. And maybe I will move on to define the stability. Okay, so stability is very important not only for signals and systems, but also for every system with a controller. You have to design a controller to make the system stable and do the right thing. Okay, so stability is a very big issue. Therefore, there are a lot of definitions in various textbooks, but I think for our class, we will think of one definition, which is called bounded input, bounded output, also known as BIBO. So there are a lot of definitions, but I would write down the stability as for every bounded input. So if input is bounded, then the output is bounded. If this is true, then the system is called stability. Okay? And there is like bounded input and a bounded output, so this is called BIBO in some textbooks. So if output is bounded, then there's no divergence, so you can say that this system is kind of stable. And there's very famous example, which is called an inverted pendulum or pendulum, to describe this definition of stability. So there's a pendulum here in a normal way. So this is a wall. This is a wall, and if I have a pendulum here, and this is a pendulum, and also I want to compare this with the inverted pendulum. And now we are talking about this angle here. This angle from the vertical line. And so if you look at this pendulum in a normal way, then if you have a slight displacement, okay, if I have a slight displacement like this, and due to the gravity, that this pendulum will act like this, and it stops at the origin. Okay, so the angle here becomes 0 with this pendulum. So if I have some input which is bounded, okay, then the output of this angle for the pendulum will decrease to 0, converges to 0 due to the gravity, which means that output is bounded. So for the pendulum case, the movement of the angle, which is an output, is bounded as time goes on. However, what happens if I have a slight input? I mean, if I have a slight displacement of this angle for this inverted pendulum, then with a slight angle, even though it's a slight angle, a very small value, you will have this pendulum fall to the ground because of this gravity effect. Therefore, with this example, with this definition, with the bounded input of this inverter pendulum as an angle, the output is not bounded but diverges to become a larger value. So with this definition, we can say that the pendulum is a stable system and inverted pendulum is unstable system. This is a popular example to describe the stability of the bounded input and bounded output. What about, okay, let's think about a integration one more time. Okay, is an integrator stable system or unstable system? Can you think about it? if I progress this integrator system with a step input, step function, step input, then obviously this step input is bounded, right? So it does not diverge. So if I have like a limit here and virtual limit here, then this step input is bounded, right? So it does not diverge like an exponential function. If I give an integrator this bounded input, what happens with the output? It's the integration, right? So if you just integrate 1, then then you will have a polynomial function of order 1, right? So the output would go like this. You just do the integration. Then maybe this function is called ramp function. Even though we had a bounded input, the output is not bounded because it diverges as the time goes on. So we cannot say that the output is bounded. So in this case, the ramp signal is not bounded. And with this example, we can say that the integrator is not stable. No, I'm just gonna say it here. Unstable or not stable. Okay, I think I'm gonna move on to the last two properties. We have come up with a lot of properties here, starting from memoryless, and then invertibility, and causality and stability. And I want to introduce two more, which we have already mentioned in the introduction chapter, which are time invariance and linearity. So these two are very important because we will deal with LTI system, linear time invariance system. Of course, the other properties we have come through are important, but if someone asked me to pick just two of them, which is the most relevant to this class, are the ones that we're gonna study about right now, which are the time invariance and the linearity. And I think we already had the definition, but I will write down one more time. So I think the time invariance means that if you have a system, a normal system like this, then if you shift the input by t0, then this affects the same as shifting the output by the same amount. So I think you will get it if we have some examples, as we always did. Okay, I'll start with the accumulator. in discrete time. So if we do the summation from minus infinity to n, of the input, by the way, this is called the accumulator. So this is similar to the integrator in continuous time, correct? And if this, can you say this accumulator time invariant system? Of course you can, because so if I want to accumulate only up to n minus 1, if I want to accumulate by n minus 1 and modify this this input function here, then it will have a same effect on shifting this output here. So definitely the accumulator is time invariant. On the other hand, let's talk about this sample, one more example here. So now the output, we have this system which is you have to multiply the input by the sine t to get the output. And if we shift the input by t0, which means we have to put xt minus t0 into this input here, then the output would be like sine t. Sine t is not affected because we only shifted the input signal here. So the result will be sine t multiplied by xt minus t0. Okay. However, if we want to do the output shifting, which we can write down as this, then what we should do is we have to replace all of the variable t here with t minus t0. So if I do that, then I will have sine t minus t0 multiplied by also t minus t0 of the input. So can you guarantee that these are same? No, you cannot guarantee that these are same because of the input of the sine function. Therefore, this system is not time invariant. Can you see the difference here? So it's kind of convenient to distinguish whether if it's time invariant or not. You just plug in the shifting effect for the input and also for the output, and you just compare, and you can see that if they are equal, then it is time invariant. If it's not equal, then it is not time invariant, or time variant, you can say. So this was about this time invariant, and then finally we will have linearity. Okay, the definition of linearity, I'm not gonna write down the statement, but I will just stick with this equation. So I need two systems to deal with linearity. So x1, if I have a system of x1 and y1 for input and output respectively, and then another system excuse me, we will have this we will have a same system, we'll have the same system but two different inputs. I'm very sorry about this. So to deal with this linearity, we need only one system to describe whether if it is that only system is has linearity or not, but we have to have two inputs to describe it. I'm very sorry about that. So then here comes the definition, the most important part. Then the linear combination of the inputs. Okay, so if you do the linear combination of the inputs, this is the linear combination of the inputs with A and B being constant. So the linear combination is like if you multiply the signals with the constant value, and if you add all that up, then that's a linear combination. If you process this linear combination of this input, then you will have the same result as having this output of each signal and doing the same linear combination. So this is the same as So this is same as you process this each signal first, this input first, and then perform the same linear combination, and you will have the same result. That's the definition of linearity. So one more time. The output of the combination of the inputs results in the same linear combination of each output for each input signal. Okay, let's have an example here. I think I'm gonna have yt equal t times xt. Okay. So I need two inputs, two signals. So I will have one for this and the other for x2, y2. And I would like to do the combination here to make the combination of the input. So I will have let x3 as a linear combination of x1 and x2 with the help of this constant value x, a and b. And if I progress this x3, so we are now doing we're now performing this input. We are processing this input here. Then it'll result y3, which is by the definition t x3. So from here to here is just the definition of the system of this example. And then I can say that with this relationship right here, I can say ta x1 plus t b x2 with the linear combination of the inputs. And if you carefully look at this equation here, we can say from this one and this one is y1. So this is y1, and this one right here and this one right here, we can say also as y2. Okay? Therefore, we can modify this equation as a y1t, excuse me, and b y2. So having the linear combination of the input is the same as doing the same linear combination of the each output. So we can say that this system is linear. Now let's have an example which has a square on it. And we have a pretty strong feeling that this system is not linear, but let's prove it through the same progress here. We already know that this is not linear, but let's do it anyway to see what happens if we do the similar thing here. So y1, I would get x1, and y2, we do the same thing with the definition of this example. And if I let x3 as a combination of these two inputs, now let's figure out what y3 is. So y3 is x3 squared, okay, with this definition. And then I have to multiply this by itself to make it work. And if I do that, I will get this. And by looking at this ugly stuff, I want to do this kind of thing, and I find out that this one right here is y1, and this one right here is y2. But I cannot move forward. We cannot do any more stuff with this definition to replace it. So this thing here, we obviously cannot make this linear combination of each output. We cannot do it due to this term here, and also they are squared in both A and B, so it is not possible. Therefore, we cannot make this AY1 plus BY2 as we did in the previous example, and therefore we can conclude that this is not linear. Okay? So we all know that the x squared is not linear, but you have to know how to do this progress to see that this is not linear. Okay? Okay, so these were about the system property. So we have learned about system property, and now we will move to the next chapter, which is about the convolution. So we finally wrapped up the chapter 2, and now we will start chapter 3, which is about a convolution. There's assumption that we will talk about this LTI system only. So assumption is the system you're talking about are LTI system, which stands for linear time invariant system, which we have just covered here. So the system we are talking about for chapter 3 are time invariant, which satisfy this relationship, and also it's linear, which satisfy this relationship right here. So with this LTI system, we are gonna make some strategy which uses the time invariant property and linearity property. And the basic strategy stuff that we are trying to do here is two things, which is about decomposing the input signal. So we will now decompose input signal into a linear combination of basic signals. So like we can have any input signals, any random input signals, but we will decompose it to have a combination of basic signals. And what are basic signals? We have to design or choose this basic signal which provide us a very convenient analysis. So these two are basic strategy that we're gonna do here. So we decompose the input signal into the linear combination of the input signals, which provide us a analytic convenience. And we have a great input here, which are appropriate for the analysis, and those two inputs are called the delayed impulses. We know what impulse function is, right? So these two are delayed impulses and the complex exponential. We're gonna study both of them. The first one, if we go through the first one, then this delayed impulse as a basic signal will give us the definition of the convolution. So obviously from the title of the chapter, we will deal with the delayed impulses in this chapter first. And if we go through these complex exponentials, then we will end up with the Fourier analysis. So we are planning to deal with these delayed impulses first in this chapter, and we will study about this Fourier analysis in the near future. Okay? So since we are studying this one, let's talk about these delayed impulses. Okay, so I think I'm gonna import a picture, which is also in the PDF that I uploaded in AjuBB. I think this one is. I think something's wrong with this GoodNote app. Okay, I get it. Okay, now it's about this delayed impulses. So why there is a word delayed here? Because okay, I think we have studied this already. And what happens if we have a delayed impulse? When we introduce this unit impulse function, and when we are dealing with the relationship between this unit function and impulse function, we have already did some delayed version of the impulse. So we had this figure here, we plot it together, and if you just have delta n, you will have the value 1 at 0, but if you have delta n minus 1, you will shift this value 1, the only value 1, from 0 to 1. And similar thing happens when you change this number. So if I have like delta n minus k, then you will have the value 1 at k and 0 otherwise. You get it? So we already talked about this delayed impulse. Of course, we haven't used the term delayed, but obviously you know, because this is like shifting. By the way, we talked about the unit delay at the beginning of this lecture. So we already know what these are and what they do. And we decompose this input signal. So this is a random input signal here. Which is ugly. And I want to decompose this input signal here into the linear combination of basic signals. And the basic signal is delayed impulse in this chapter. So I want to focus on the linear combination first. So I mean, if I have this input signal, but if I decompose, like if I want to deal with this only for the first time, and I just want to deal with this for the second time, and if we do that for the third time now here and the fourth time here, and we do the summation of these, then we will get the original input signal, right? So this was about the summation, about the linear combination. And now if you see each of these, then you can express this x0 as the value of x0 times this impulse function. Can you see it? So this represents the height. This represents the height, the amplitude of this discrete signal. And this delta n makes this height at the correct position, which is 0 here. With this, okay, so this one was about this. And if you analyze this x1 here, you have to look for the third plot here. And this x1 represents the height of this a signal. And now we have to have delta n minus 1 to represent, to make this x1 to the position of 1, not 0. So we have to move. You have to shift. Or you have to use the delayed impulse to make this signal here. So this one corresponds to this one. And also please note that the delta function has the value of 1, so obviously this it makes this variable x0 as the total amplitude. So if I multiply this x0 by 1, it also gives this x1. Therefore, all the information about the amplitude is right here. This only gives the location of the discrete time for each signal. So if we proceed this step for the rest of the input, then I think you will have this kind of infinite number of summation. So the first one here is right here, and the second one right here, and the third one maybe. We haven't done it, but we know it's the same progress. And we can combine these all together by utilizing this summation function. So inside the summation function, the variable refers to k, and as k changes, the amplitude of each delayed function also changes. So we have k here because this x0, x1, x minus 1 changes, and also we have to put k here because the thing added to the n also changes from value to value. So if you carefully compare this one and this one, we can like make this infinite number of summation, which is linear combination, to this. So the first strategy to have a linear combination of basic signals is this one thing. The first strategy means this. We will have the input signal as a combination of basic signals. And basic signal here is the delayed impulse. Okay. So obviously we are dealing with discrete time first. Oh, I haven't mentioned. We will start with discrete time because you can have more easy approach. So if I write this equation down, because this is an important one. So xn, we can decompose this input signal into a linear combination of basic signals, which can be represented in the equation with the help of this summation from minus infinity to infinity, where xk times the delayed signal, which is, the basic signal, which is a delayed impulse. So this one is like the basic signal, as I have told you many times. And this almost looked like a coefficient, right? Because when we talked about this linearity here, that xk was like this a and b. So this is like almost a coefficient in the polynomial nominal function. And so this is like the result of like decomposing all this input to represent it as a basic signal to have a linear combination. And now we are gonna deal with this this input signal by this form and use the LTI systems. I'm gonna use the linearity now. So as we have assumed LTI system, at first I will use the linearity to deal with this the combination of basic signals, and then we will use the time invariant to make things easy to get the definition of convolution. So as I said, I'm going to use the linearity first. If you view the definition of linearity again, then we can say that again. I've already done this, but I will speak it one more time. The output of the linear combination of inputs is equivalent to the linear combination of the output of each input. So I will use that property first so that we're gonna see what happens to this decomposed signals, and then we will apply the property of time invariant system to define this convolution. However, I'm not gonna do it today because I think we have done a lot of things. And we are running out of time. So please think of the properties we have been through today, the systems property, and the basic strategy that we are going to stick to for chapter 3 or more, which is about decomposing the input signal to the combination of basic signals. And we will have 2 basic signals for the entire class. And the first one was about delayed impulses, which will result a convolution, which is also the title of this chapter 3. Okay, thank you very much for today. If you have any question, then please email me. And thank you for your attention.